Part of the reason I love testing hotel rooms is that it's a microcosm of what's going on in our homes day to day. And you can actually explore all four of the elements of home performance in this example, which are heat bleed, airflow and pressure, moisture, and contaminants. Heat bleed, infrared camera, airflow and pressure, manometer, which is a pressure gauge, moisture, here and here, and contaminants, which would be all of these. And by the way, if you need any help with this book is specifically, this is what I wrote it for, is for testing like this. And I'm actually using that to do a calculation that I don't keep inside my head. So quick tour, hallway, walk in, big room, HVAC system with the thermostat on the wall between the return and the supply. And by the way, these two being so close together means it is possible and likely that we're gonna have a little bit of short cycling here. Small room over here. And this is obviously gonna be one of the most occupied rooms for long periods of time. Now here's the funny thing about this. Take your infrared camera, and we look at where the conditioning device, which is this heat pump, is. We have this wall over here, which has an exposure to outside. But actually, it turns out, even though this room is bigger than this room is, that the exposure to outside is bigger in this room. We've got two exterior walls here, not just one. So technically, if we were doing this right, we would have the conditioning in that room because it needs it more. But this is the central room that the bathroom opens off of as well. So like, yeah, it kind of makes sense that they put it in here. It's the main living space. Now they did two things that I think are a little bit funny here. That is a French door that's got glass in it. So when I close this, this is like not to do with home performance, although we are able to test light. Like, I don't know why that helps whoever's in there. If I'm up in the middle of the night watching TV out here, seems like that should be a solid door. But also we've got that. And this is what they are attempting to do to make up for the fact that, yeah, that room needs cooling or heating more than this room does actually. So we can take a look at what this is. This is a through wall exhaust fan. And this is something that I actually recommend to a lot of my clients, which is that you don't need to add a mini split to that room. You do not need to add an ERV exhaust in that room if you're thinking about an ERV system. What you need to do is move air around, because of the 5 factors of ventilation, the number 1 factor is circulation. We gotta move this air around. And so this does that. Now this is not a very good solution for this because of this. Can you imagine sleeping with that sound by you all day long? And by the way, I tried it at all the speeds, and it's annoying at every single one of them. Which must be why they give us this sleep sound machine. When we pull up this fan online, this is a Broan model 510 or 511, we can see that it's specified to have either 370 CFM or 180 CFM of flow. So let's go find out. And by the way, this Sones, these are both real loud. 8.5 Sones is very, very loud. This is a system that was developed to try and make sense out of decibels so that we could just use it for human hearing. So the way that I want to test this is with a whole of known size test. So this is basically an exhaust fan, right? So this is the exhaust side of it. The air is moving through that way into the bedroom. And what we can use is, this is a static pressure probe. This is just to keep directionality out of the equation. And I know for a fact that this thing can't reach the fan blades. So always check that. Don't do this at home, kids. And now what we can do is simply, we check ourselves, yeah, 0. And now that we're running, we've got the pressure reading in there, 19 pascals. Now, does the pressure change when we close the door? That's an interesting question. Oh, interesting. So we can drop the airflow if we close that door. Now, before we start investigating the pressure that's going on in that room that might be causing that, let's see what we got going on. So we got 15, 16 at the low end, and 19 at the high end. In the exhaust fan flow section, I teach you how to make your own box that would look like that. That's basically what we're using here. But instead of a box for area here, we're gonna use this 8-inch duct that the fan is built into. So we're gonna use an 8-inch duct cross-sectional area, which is 50 square inches. We've got the square root of the pressure times 1.075, 234 CFM, which means that this thing probably is not that. Although this test that I just ran is pretty ridiculous. It might be that, but the fan is just so dirty and so old that the motor is not running right. And then when we shut the door, it dropped. It seems to have dropped down to about 215 CFM, which is significant. So let's find out why. So this is your 1-channel manometer. Again, this is $400. Got magnets on the back, which is why it's floating here. We've got 2 ports down here. We've got positive and negative. We can call this input and reference. If we want to know what the pressure in that room is with reference to out here, when we hose it up like that. And then we take the end of our pressure hose, throw it in the room, and then we close the door. So that the hose is in the room and we are out here. You always want to know what you expect to see before you run any test. What we'd expect with the fan off right now is that that room is 0. That room seems to be depressurized, but there's no fans in that room. So likely what's happening is that we're actually pressurized in the room that we're in. Somebody in the hallway is getting really creeped out right now. So it looks like the hallway is depressurized with reference to, again, you always want to know how to say this. The input is in the hallway with reference to the hotel room is depressurized. And that's weird because normally a building like this would be supply plenum in the hallway. So they would be supplying for the hallway and then drawing from the exhaust fans in the units. But this one, for some reason, something out there is depressurizing the hallway, and it might be that that is stack effect at work. We are on the top floor of this building, but it's not a huge amount of depressurization. What it means is that no air is coming from the hallway into my unit, and I do like that. And last, contaminants. So I just ran our 6-channel particle counter, and it looks like we're in the green. We have no huge particles. We've got some PM5 particles. We've got a few PM2.5. We've got more, 1 micron, 500 nanometer, and 300 nanometer. And this is where a HEPA filter is gonna grab all of those and all of these along with it. So if we had a better filtration system in this room, that would be great. We don't. Deal with it. But what I think is also interesting, aside from the fact that we're in the green, which is good, is that we've got 70.9 degrees Fahrenheit, and we have 53%. By the way, it's telling you also what the dew point and the wet bulb temperature is, and those are all interesting numbers. So you got 71 at 53. If we come over here, we can see 70 at 51. We can see 70 at 53. We can see 71 at 53. So all of our devices are agreeing about the temperature and the relative humidity, and that is a good thing. Here we've got the carbon dioxide. This is the AirNet 4 carbon dioxide monitor, and you can see this is the homemade case that I made. I take this everywhere with me. And I'm not looking for a particular number. What I'm doing is tracking the curves, the arcs through time. And overnight in that closed room, without that fan running, it was pretty reasonable the whole night. It was a very reasonable arc. So it all stayed around this 1,000, 1,200 level. We also have here radon for the first time. This is the first video I'm making with this radon monitor. And we've got 1.22 picocuries per liter. That's probably a little higher than it is outside, but we would have to go outside to know that. This is a really cool tool because it's brand new, first of all, it's huge, but also it gives you a reliable reading within an hour. So I've started this running less than an hour ago and it's still refining its 1 hour data. We have temperature, relative humidity, and light here, and that is useful because if you want to put this someplace and then find out when the sun came up and went down or when people were in the space occupying it, you can kind of track against daylight or occupancy in a room that has no window with this kind of a thing, so that you could then take this number and be like, oh, the reason that that was here because somebody was in the room, they were using the light. And then here we've got radiation, and I'm gonna be experimenting with this, but this would be from radioactive products that you might have in your home, which would be mostly used old stuff, Or I've heard of places being built with like concrete from the wrong mine, and it actually causing radon because it's the concrete is radioactive. So I'm going to experiment with this. This is a fun little extra tool that I've got in my bag. It was brand new also. You want this number to be between 0.2, like below 0.2 is better. The medium contamination level will be between 0.2 microsieverts per hour and 10. And then anything above 10 would be like danger zone. So let's all be aware of the dynamics around us, the changing nature of how things work. We do not live in a static world. We live in an ephemeral one that's always different moment to moment. And I just think that's so beautiful. So happy testing. Tune in next time.